Listen, pull up a chair. Today, I'm putting on my senior engineering mentor hat. We're going to look at exactly why that naive AI prototype you probably built in an afternoon will inevitably break the second it hits the real world. I mean, I cannot tell you how many times I've seen a junior dev ship a basic wrapper around a prompt, only to watch the whole system completely crash when a real user tries to actually have a multi-turn conversation with it. So today, I'm giving you the practical step-by-step how-to guide for engineering resilient, production-ready AI systems. So why do they fail? Well, it's the ultimate reality check. Writing a simple prompt in a web interface feels like absolute magic, right? You type a question, you get this brilliant answer back, and immediately you're thinking, wow, I can build a startup around this. But the absolute minute you plug that into an automated workflow with thousands of angry concurrent users, things burst into flames. Building a system that actually survives unexpected data, handles dropped connections, and, importantly, doesn't bankrupt you in variable API costs, that is where true engineering actually begins. Here's our game plan for this session. We're going to cover the zero memory problem, engineering state, beating the token bottleneck, enforcing structured outputs, putting it all together in a stateful master blueprint, and finally, scaling to production traffic. All right, let's dive right into part one, the zero memory problem. Okay, so here is the biggest illusion junior developers fall for. Large language models possess zero inherent memory. None. Zilch. The model doesn't remember you, it doesn't know your preferences, and it literally doesn't even remember what it just generated 5 seconds ago. It's kind of like talking to someone with severe amnesia. Every single time you speak to them, you have to remind them of exactly who you are and everything you've talked about up to that very moment. Memory in AI? It's basically a parlor trick. We create it by explicitly injecting your entire interaction history into the payload every single time. If you just ask an isolated follow-up question like, hey, can you simplify that? The model crashes because it has no clue what that is. It's a classic stateless failure. You have to engineer the state by prepending the prior conversation. And this is the vast difference between just playing in a sandbox and building a real working app. Singleton tasks are just isolated experiments. They take an input, give an output, and then they die. Basically a glorified search bar. But true conversational systems, they demand dynamic context. They require strict memory management and automated loops to keep the lights on across multiple interactions. You aren't just writing prompts anymore at this stage. You're engineering a persistent state machine. Because a production system doesn't just fire off isolated commands. It relies on continuous dialogue loops. As a developer, you have to dynamically maintain that context from block 1 of your application straight through to block 2 and so on. You have to actively manage the memory limits, catch unexpected outputs algorithmically, and just weave the whole shebang together. It's a continuous engineered loop. If any single link in that chain breaks because the model lost context, your entire application goes down. Moving right along to part 2, engineering conversational state. To actually build this persistent pipeline, you need a strict cast of architectural characters in your code. Think of them as the 3 core pillars of your payload. First, we have the system message. I like to call this the architect. This sets the global behavior, the persona, and your strict unbreakable constraints. Second is the user message, the input. This is the human, or maybe an upstream app, driving the interaction with raw data. And third is the assistant message, the output. This is the model's response that you absolutely must capture, save, and inject back into the next prompt to maintain future context. So let's look at how this actually maps to code. Every engineered payload requires these specific characters to be mapped to a strict JSON structure, which, if you aren't familiar, is just a standard text-based format we use for representing structured data. You do this right before hitting the API. The system message sets the unbreakable rules, like always respond in JSON format, while the user and assistant messages stack up chronologically right below it. This structured payload is the literal foundation of stateful AI. Without it, you just have a noisy amnesiac text generator. All right, part 3, beating the token bottleneck. This is where things get real. See, stacking up all this history introduces a really harsh physical constraint. Every single model out there has a strict maximum token limit. You can just think of a token as a piece of a word. When all those past messages try to cram into a tiny context window, they spill over. Unmanaged long conversations are going to inevitably exceed those limits. Best case scenario, the API simply rejects your request and throws an error. Worst case scenario though, the model quietly drops the oldest messages, and if those oldest messages happen to be your vital early system instructions, well, the AI goes completely rogue, breaks your formatting, and starts outputting garbage. Plus, processing that massive context window starts driving up your operational costs exponentially. So to fix this, production systems divide memory by storage location and retrieval latency. We use short-term memory, which is the recent history appended directly to your prompt for ultra-low latency, and then we use long-term memory, like the vector databases used in RAG, or Retrieval Augmented Generation. RAG essentially lets the model search an external database for relevant facts instead of you trying to cram a whole encyclopedia into the prompt itself. But managing this, it forces a constant engineering tug-of-war between cost, latency, and context coherence. Including more history definitely gives you much better, more coherent answers, but it slows down generation time significantly and spikes your API bill. Because of these trade-offs, you absolutely must selectively prune your conversation history. You essentially have 3 strategies in your toolkit here. A sliding window just simply drops the oldest messages. Super easy to build, but you have a huge risk of losing those early instructions. Summarization uses a secondary, usually cheaper AI to compress old messages into a dense paragraph. It's highly efficient, for sure, but subtle nuances lost forever. Or, my personal favorite for complex enterprise apps, priority-based retention. This locks in essential instructions while flushing out casual chatter. It definitely takes complex engineering to score and rank message priority, but it is virtually bulletproof. Okay, part 4, enforcing structured outputs. If you want your system to actually survive an automated workflow, you need an enforcement protocol. Raw, unstructured text will instantly break your downstream APIs. So, step 1, your system prompts must explicitly demand an exact JSON format. Step 2, you have to provide few-shot examples within the prompt itself. That just means showing the model exactly what success looks like with sample inputs and outputs. And step 3, aggressively ban conversational filler. Believe me, you do not want your automated database parser receiving a message that says, "Sure, here is your answer, buddy," right before the actual data. It will crash your entire pipeline. The absolute golden rule of AI engineering that I teach all my juniors is this: never, ever trust raw output. Resilient architectures deploy automated validation loops. Before an LLM's output ever reaches the end user or triggers a database update, it has to hit a programmatic validation check. If there's a formatting error, a missing bracket, or an obvious hallucination, it triggers what we call a fast-fail retry mechanism. The system automatically fires a prompt back to the model saying, "Hey, your output is invalid. Regenerate incorrect JSON." This all happens in milliseconds, completely invisible to the user, ensuring only pristine data moves forward. Part 5, the Stateful Master Blueprint. Let's put it all together. Here it is, the master blueprint. This is how you actually engineer a stateful, resilient architecture. Let's trace the heartbeat of a production system together. We start at step 1. The user input triggers the event. Step 2, we execute the history append, merging that new input with our short and long-term memory stores. Step 3, we apply context truncation to make sure we stay perfectly under that strict token limit. Step 4, the API call actually executes with our strict architect constraints. Step 5, the validation check runs our fast fail loop to guarantee we got that structured JSON output. And finally, step 6, we write the successful response right back into memory, perfectly primed and ready for the next cycle. Finally, part 6, scaling to production traffic. Taking that master loop we just looked at from one single user to 10,000 simultaneous users, that introduces massive infrastructure headaches. You now need incredibly robust session management. Your backend has to partition and route distinct memory streams simultaneously. Think about it. If user A's memory leaks into user B's context window, that is a catastrophic security failure and a massive privacy nightmare. Plus, processing those structured formats and constantly retrieving long-term memory adds serious overhead, demanding strict latency control just to keep the application feeling responsive. And this brings us to a really hard truth of senior engineering. Developers must aggressively limit prompt length and cap output tokens to control variable API economics. When you're running at scale, an unoptimized context window doesn't just cause lag, it literally hemorrhages money. Every single token is a fraction of a cent. Multiply that by thousands of concurrent users and continuous conversation loops, and sloppy memory management will break your startup's budget before you even realize what's happening. So, I leave you with this final challenge. It is time to abandon those fragile, stateless prototypes that only work in a pristine sandbox. You now know the mechanics of the zero memory problem, you know how to engineer conversational state, how to truncate context to beat the token bottleneck, and how to build automated fast fail loops. The blueprint is officially yours. So the only question left is, are you ready to actually architect for production? Thanks for joining me for this explainer, and I'll see you in the next one.